Hello and welcome to the AICE Chemistry Lecture Series. Today we're going to go over Chapter 8.4, which is going to cover equilibrium and the equilibrium expression and the equilibrium constant, but as it relates to gases and pressure. A lot of this is going to pull back from 8.3, where we learned about the equilibrium constant, but we're going to now look at how all of that applies to reactions which only have gases in them, and therefore we can use pressure instead of concentration. Now, before we start talking about equilibrium, let's talk about the units for pressure and a few different details about them. When we have a mixture of gases, which we will have when we do equilibrium, we're going to look at what we call partial pressures. For any reaction involving nothing but gases, it's usually going to be easier to use pressures as an indicator instead of concentration because it's very easily measured. The pressure of a gas is always going to be related to its concentration. And that's because what affects pressure are the number of moles of a gas as well as the volume of the container. Those two things are also the two measurements that affect concentration. So we can change the pressure of a gas without changing its concentration. And therefore, pressure and concentration are related to each other. They have the same trend. If pressure goes up, so does concentration. Why? Because that means that volume either went down or the number of moles went up. Inversely to that, if pressure goes down, then the concentration also goes down. And the reason for that is simply that in order for concentration to go down, one or two things needs to happen. Either the volume of the gas needs to go up or the number of moles needs to go down. And so if we increase our volume or decrease the number of moles, it will decrease concentration, but it will also decrease the pressure of that gas and vice versa. Like I said earlier, the only way to increase pressure is to either increase the number of moles of a gas in a container or decrease the volume of the container, which will also inadvertently increase the concentration. So we can use pressure instead of using concentration when it comes to gases because it's a much easier thing to measure when it comes to a reaction where it's all gases. Now, in order to do this, we do have to have a reaction that is all gases. It can be some gases and some liquids, some aqueous. It has to be all gases. Now, the issue is going to be when we have a mixture of gases, like we do in equilibrium. When we have a mixture of gases, when we record the pressure of that mixture, we are recording what we call the total pressure. That's the pressure of all of the gases mixed together. Each gas contributes its own individual pressure to the mixture, however. And the number of moles of that gas are going to affect how much pressure it contributes. We can look at the individual pressures of the gases with something we call partial pressure. Partial pressure is the pressure exerted by a particular gas in a mixture of gases. So, for example, if we got gases A, B, and C all mixed together, the pressure that A contributes to the total pressure of the container, that's the partial pressure of gas A. So each individual gas is going to contribute pressure to the mixture. Remember, pressure is just the particles of that gas bouncing on the sides of the container. So if we have a container with nothing but gas A, then the pressure in this container is the pressure that gas A is contributing. If we have a container with nothing but gas B, then the pressure in this container is just the pressure from the particles of B bouncing on the container. But if we have a mixture of both gas A and B, then the pressure in this container is an addition of the pressure exerted by the particles of gas A, the green ones, bouncing against the sides of the container, plus the pressure exerted by gas B, the blue ones, bouncing against the sides of the container. So how can we relate total pressure to partial pressures? Well, the total pressure of a gas is going to be equal, total pressure of a mixture, should I say, is going to be equal to the addition of the pressures of the individual gases in that mixture. So if a mixture of gases is made of A, B, and C, then the total pressure in that container is going to be equal to the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C, so on and so forth, depending on how many gases you have. So in this example right here, if we had a container with nothing but gas A and a container with nothing but gas B, and these containers were the exact same volume, right? So this had to be the exact same volume. If we were to now grab all of these gas B particles or moles and put them into a container with gas A together, this mixture will have a total pressure that is equivalent to the partial pressure that gas A had plus the partial pressure gas B had. So if gas A had a partial pressure of 8 pascals by itself, and gas B had a total pressure of 3 pascals by itself, then to get the total pressure in the container where they're mixed, all we will have to do is 8 plus 3, or 11 pascals. So this is what partial pressures are. Partial pressures are the pressures of the individual gases in a mixture, whereas the total pressure is the mixed pressure, the pressure of all of the gases mixed together in the same container. In order to do this math, though, just keep in mind all of the volumes of the containers need to be equal. So if this contains 1 decimeter cubed, then this container has to be 1 decimeter cubed in volume, and this container has to be 1 decimeter cubed in volume. Let's keep moving on. So because the partial pressures are essentially going to be related to concentration for any gas, when we have a reaction that has nothing but gases in it, we can use partial pressures instead of using concentrations. The equilibrium expression based on pressure is written in the exact same way we wrote the one based on concentration, with two real main differences. First of all, we're going to use PA instead of A in brackets when we write the equilibrium expression. This is to show that we're using the partial pressures of the gas and not the concentration of the gas. Apart from that, though, it's still the products over the reactants, just like we had before, with their coefficients as an exponent. So here we're still going to have the products, or in this case, ammonia. And in the bottom, we're still going to have the reactants, in this case, nitrogen and hydrogen. And you'll notice that we still have that squared for the ammonia because of the coefficient. We still have that to the third for hydrogen because of the coefficient. And the nitrogen still to the first because of the coefficient. So it's still products of the reactants with their exponents being their coefficients. The only difference is that instead of doing brackets NH3 to show concentration, we're using PNH3 to show pressure. This can be written a few different ways. Another way to write this would have been to say P NH3 and then use parentheses to the second power. I prefer this a little cleaner, but it doesn't really matter which way that you choose to show, as long as you're using that P instead of the brackets. So we could have done like this as well. This is my preferred way of showing it just because the parentheses kind of make it cleaner, but this would totally work as well. Now, the other difference when it comes to the equilibrium expression when it comes to partial pressures is that we're no longer using Kc. Now, K is the equilibrium constant, but Kc is the equilibrium constant when it comes to concentration. That's what C is for. So the Kc is the equilibrium constant when using concentrations. Because we're using partial pressures and not concentrations, we're going to use the symbol Kp, or K, the equilibrium constant, used with partial pressures. The numbers are going to be different. Kp and Kc are going to be different numbers for the same reaction. We could do the Kc for this reaction, but because everything's a gas, we can also use Kp. They're the same ratio, but different numbers. This is still the products of the reactants, so their coefficients as an exponent, but because Kp and Kc use different units, meaning that Kp uses the pascals because we're using partial pressures, whereas Kc uses moles per cubic decimeter because we're using concentration, we are going to have different numbers come out as a result. So Kp and Kc are found in the same way, but by using different units, we get different numbers. So let's look at an example of its use. But everything else, everything we did with the within section 8.3 is still going to apply. We can still do AICE tables with this. We can still use it to find KP or to find one of the missing partial pressures. It's just the exact same thing using a different unit of partial pressure for reactions that are completely gas-based. So let's look at an example. In another equilibrium mixture, the partial pressures are shown below. So we have the partial pressure of nitrogen, hydrogen, and ammonia in the reaction that we just saw, with their partial pressures being 2.20 times 10 to the 6th, 9.62 times 10 to the 5th, and 1.40 times 10 to the 4th pascals, right? Because we're using partial pressures here. And it says here, I'm going to highlight this, in another equilibrium mixture, meaning that these are partial pressures at equilibrium. Remember that according to what we learned earlier, we could have partial pressures initially and then we'll have to use an AICE table. But these are all already equilibrium mixture partial pressures, meaning that these are already at equilibrium. We can use it in the equilibrium expression. Write the expression for the equilibrium constant, Kp, for the production of ammonia from nitrogen and hydrogen. So this is going to start with finding the equilibrium expression. This is again like we had in 8.3, a multi-part question. So we start by writing our expression for the reaction that we just saw. Now, this reaction, which we'll talk about in the next section, is called the Haber process. And it's a reaction you're going to see a lot and you should start getting used to because it comes up on the AICE exam a lot. And ammonia is made by, let me do a different color. Ammonia is made by nitrogen gas reacting with hydrogen gas in an equilibrium reaction to make ammonia, NH3, which is also a gas. This is the industrial way of making ammonia, which we'll talk about in section 8.5. But we are going to see this reaction a lot. So it is a reaction that you should probably keep in mind and probably memorize. But by looking at this, in order to write the equilibrium expression, remember, all we have to do is use the exact coefficients for each one of the products, put them at the top as exponents, and then for the reactant, same thing in the bottom. But because we're looking for Kp, the equilibrium expression constant Kp for the production of ammonia, we're not going to use brackets here. If you use brackets, you would actually get this question wrong. We're going to use the P with our exponent. So I'm going to do it with the way that the book does it. So P to the second NH3, because 2 is the coefficient for ammonia, and then over P to the first for N2, because coefficient for N2 is 1, times P to the third for H2. And that's my equilibrium expression for our Haber process, or for this reaction here. Obviously, we're going to keep using this in following questions in order to then find Kp because they're giving us these numbers. But for question 1, all they asked us to do was write the expression. They did not ask us to use the numbers yet. That is going to come in a later question. Now, before we go to the next part of this question, part 2, let's talk about the units for Kp. Now, this is going to be a very similar conversation to the units for Kc. However, we need to realize that the units are going to be different because we're not using concentrations. Just like Kc, though, Kp can have variable units. It can have varied units that we're going to have to figure out for each reaction we do, for each problem that we do. But for Kp, we don't use moles per cubic decimeter. We use pascals because we're using partial pressures. So the units for these partial pressures are going to be in pascals, meaning that when we do something like this is a reaction that we're doing in 8.3. P squared Hi over pH2 times Pi2. When we do this reaction, we want to find the units for Kp. What we're plugging into here is no longer moles per cubic decimeter. because we're not using concentrations. We're using partial pressures. So with partial pressures, instead of putting moles per cubic decimeter here at the top, we're going to put pascals squared. Over Pascal times Pascal, these units are going to end up canceling each other because we end up with Pascal squared, and we get no units for this KC. So this is exactly like we did in 8.3. We're still just plugging in the units instead of the numbers and then figuring out what cancels or what doesn't. But it's actually a little easier because instead of dealing with a compound unit like moles per cubic decimeter, we're dealing with a single unit, which is pascals in this case. So it's a lot easier to see that pascals times pascals is going to give us Pascal square. So Pascal square cancels each other out and gives us no unit for this particular KP. And I should say P here, not C. This KP, that's the typo. But yeah. So let's look at an example of this. So if we, this exact same question we were just looking at, again, these are already equilibrium mixtures that we can tell here by our equilibrium mixture, and the partial pressures are shown here. And if we remember from what we did in a couple slides ago, the equilibrium expression for this is going to be that Kp is going to be equal to the P squared of NH3 over Pn2 to the first power times PH2 to the third power. So in order to figure out this, now the question is going to ask us here to calculate the value of Kp. So we need to do mathematics and show the math for the calculating the value of Kp, and we need to state the units. So we need to get the value and the units for Kp, and you'll notice this is a 2-point question, and so we're probably going to get 1 point for doing the work and putting the Kp down, and then 1 point for the units. All we have to do here, and I'm going to switch over to blue, is use this equilibrium mixture partial pressures in our equilibrium expression, just like we did in part 3 or in 8.3. However, the only difference is that these are going to be in pascals instead of moles per cubic decimeter because we're working with partial pressures. So the P of NH3 here is 1.40 times 10 to the fourth. So we're going to put 1.40 times 10 to the fourth squared, because this is P squared, over P of N2, which is 2.20 times 10 to the 6 to the first power. And then we are also going to multiply that by the P of H2, which is going to be 9.62 times 10 to the fifth power. But this one's going to be to the third because of that 3 coefficient in front of hydrogen in the actual equation. So all we have to do here is put this in the calculator. So we'll do 1.4 times 10 to the fourth power squared and then divide that by 9.62 times 10 to the fifth power to the third power times 2.2 times 10 to the sixth power. And remember to properly use parentheses when you put this in the calculator. If you don't put parentheses with all these exponents, you are going to mess this up. So make sure that when you use your calculator, you know how to use a calculator. Put as many parentheses as you need to properly separate all these scientific notations and all these exponents. And we end up with the answer here being 1.00 times 10 to the negative 16 and then for the units, let me do it in a different color. We are going to do the exact same thing, but only instead of plugging in the numbers, we're going to plug in the unit, which is pascals. So here we have pascals squared over pascals times pascals to the third. Now the Pascal square over Pascal times Pascal to the third means that we have Pascal squared over PA to the 1 times PA to the 3 gives us PA to the fourth. So the 2 cancels out with the 4 to give us 2 in the bottom. That's 1 over PA to the second or PA to the negative 2. And so that's what I'm going to put here, PA to the negative 2. So that's our unit. So again, we're going to solve it exactly how we solve the math, but we're going to put the units instead of the math here and cancel whatever we can. And so we get that our Kp is equal to 1 times 10 to the negative 16. Oops. And then our units are Pa to the negative 2. And that's it. Like, we do exactly the same way that we did Kc, only the units are different. And the symbols that we use are different. We're no longer using those brackets, we're using the P's. So let's keep going. Let me get rid of all this. So partial pressures and mole fractions. This is going to be something that we're going to use in order to figure out partial pressures. Unlike the question we just did, where the partial pressures were just given to you, sometimes you will need to find the partial pressures based on what we call mole fractions. So let's first talk about what a mole fraction is. A mole fraction is the number of moles of a particular gas in a mixture of gases divided by the total number of moles of the gases in the mixture. It is essentially a percentage. What percentage of all the total moles of every chemical in a mixture are of a specific gas? So all we have to do in order to find a mole fraction, and it is not particular percentage because we're not multiplying by 100, it's a decimal. But in order to find a mole fraction of, for example, gas A, which we'll show by using a capital Chi, which is a Greek letter, or an X, really, it's a capital X. So capital Chi with that subscript A means the mole fraction of A. In order to find the mole fraction of A in a mixture, and A could be any part of any gas in that mixture, we need to do the moles of A divided by, and remember N means moles, so moles of A, divided by the total number of moles in the mixture. Now, why is this important? Remember that the pressure is related to the number of moles of a chemical in that mixture, because the more moles of that gas you have, the more particles are bouncing against the sides of the container, the more pressure you have. And so the mole fraction can help us figure out the pressure, the partial pressure of a chemical, since they're related to concentration. If 50% of all of the particles in a mixture are of chemical A, then 50% of the total pressure comes from chemical A. It's a simple ratio. Since the concentration and partial pressure of gas are related, we can calculate partial pressures using the mole fraction. So if I wanted to know the partial pressure of A, but it wasn't told to me, but the number of moles of A were told to me, then the partial pressure of A could easily be found by multiplying the total pressure of the mixture times the mole fraction for A. So if I knew how many moles of each chemical I had in a mixture, and I knew the total pressure, I can figure out what the partial pressure of each chemical is going to be by simply using this equation. Total pressure of the mixture times mole fraction of the mixture, which we can find by dividing the moles of that chemical by the total moles in total, including of A. That will give me the partial pressure of A. The sum of all the mole fractions should add up to 1, as it is essentially just a percentage without it being multiplied by 100. It is the percentage in its decimal form. So the total mole fractions added up for a mixture should add up to a 1 round. So let's look at an example of a question that uses these mole fractions. So in this question, this is part 2 of a question. I have gone ahead to save us time and solve part 1, which is just using an AICE table. But the question says, at a pressure of 2 times 10 to the 7 pascals, 1 mole of nitrogen gas was mixed with 3 moles of hydrogen gas. The final equilibrium mixture formed contained 0.3 moles of ammonia. Now, in part 1, we figured out how many moles of nitrogen and hydrogen were at equilibrium. So from part 1, we know that at equilibrium we have 0.850 moles of nitrogen, 2.55 moles of hydrogen, and 0.300 moles of ammonia, like it says in the question. Then the second part of the question, which is the one that's important here, says calculate the partial pressure of ammonia, PNH3, in the equilibrium mixture. Give your answer to 3 significant figures. So a couple of things here. First of all, our command word here is going to be calculate, so we know we're going to have to do some math. And then this part, so we're calculating the partial pressure of ammonia in the equilibrium mixture, which means we're going to use those moles from the first question to do so and use a mole ratio. No, sorry, not mole ratio, a mole fraction. Now, the other part that's important here is this, and this is something we tend to ignore, but it can cost you a point. The question says, give your answer to 3 significant figures. We can very often, when we're doing these complicated AS chemistry questions, forget about these simple instructions, and because we get so caught up in the actual chemistry of everything and the complicated thought process. Don't get lost, so don't forget about this type of instructions, because at the end of the day, they can cost you a point. They can cost you the last point out of this 3-point question because we don't give it to 3 significant figures or whatnot. So, how are we going to do this? Well, this is actually a pretty simple process. In order to find out the partial pressure of the ammonia, NH3, if we remember the equation, that's going to be the total pressure of the mixture times the mole fraction of the ammonia in this mixture. Now, we're given the total pressure here. It says that a pressure of 2 times 10 to the 7 pascals is the whole mixture. So we do have the total pressure of the mixture. This right here is PT. What we do need to find is the mole fraction of ammonia. Remember, the mole fraction of ammonia is going to be equal to the number of moles of ammonia, which we know we have at equilibrium 0.300 moles of ammonia, over the total number of moles. How do we find the total number of moles? All we have to do is add up the moles of every compound here. So the moles of nitrogen plus the moles of hydrogen plus the moles of ammonia. And yes, we do include ammonia because it is a total moles in the mixture. So the total moles is going to be equal to 0.850, so 0.850, which are the moles of nitrogen, plus the moles of hydrogen, which is 2.55 moles, plus the moles of ammonia, which is 0.300 moles. So the end total is going to be equal to 0.85 plus 2.55 plus 0.3, which is 3.7 moles, or 3.70 to keep the 3 significant figures they've been given us. So here, moles of ammonia we know are 0.300 moles over total moles, which is 3.70 moles. The moles cancel out. The mole fraction does not actually have a unit. And so the mole fraction here is going to be 0.3 divided by 3.7, which is 0.0811. And that again doesn't have units because the moles do cancel out. And now all we need to do to find, and I'm going to do a different color, the partial pressure of ammonia is to grab the total pressure, which is 2.00 times 10 to the 7 pascals, and multiply that by the mole fraction for ammonia, which is 0.0811. And then what we get here, which is going to be in pascals, is our answer. So 2 times 10 to the 7 times 0.0811 gives us that the partial pressure of ammonia is going to be 1.62 times 10 to the 6th power in pascals. Again, this is 3 significant figures because that's what they asked us for, 1.62. And so that is our answer. Now, this is a 3-point question, right? This is not a complicated question, but it is a 3-point question. So what are those 3 points for? We get 1 point for finding the total number of moles, so for adding up the moles from CI. And again, remember error carried forward. So even had you done CI wrong, if you didn't know how to use the AICE table, then you will still need to add up the 3 numbers that you got in CI. So even if you didn't know how to do C1, make sure that you put some numbers down so that you can use them here, get that very easy pointer, just adding things up. Then we get another point for finding the mole fraction of ammonia, that 0.3 over 3.7. And then we get our final point for finding our partial pressure here. Now, do remember, this needs to be to 3 significant figures. If you do not give this to 3 significant figures, you will not get the last very easy point. So this is not the type of question that you should be getting wrong because it is easy points. Finally, let's do one more theory question and to then be done with this section. So let's look at this theory question, right? This reaction is repeated. We're talking about the exact same reaction. This is part 3 of the exact same reaction we're just looking at. This reaction is repeated with the same starting amount of nitrogen and hydrogen. The same temperature is used, but the container has a smaller volume. State the effects, if any, of these changes on the yield of ammonia on the values for Kp. So you have to be careful here because there are 2 separate questions with 2 separate answers. So first of all, we want to see and realize that the command word here is state. State the effects, if any, of these changes. Not explain. We do not need to explain why this happens. We simply need to state what happens. Does the yield of ammonia increase? Does the yield of ammonia decrease? Does the yield of ammonia stay the same? That's it. Not why it happens, just what it is. And then there's a separate question. So there's question 1 is how does it change the yield of ammonia, the concentration of ammonia, how much ammonia we have. So that's part 1, and that's answering this first line. Then part 2 is how does this affect the value of Kp? Those are different questions. The yield of ammonia talks about the concentration or total amount of ammonia. Essentially, which way does this reaction change? Or does it go to the left, the equilibrium shift to the left, or does the equilibrium shift to the right? Now, the Kp value, that's a different story. So let's start with we're going to start with the bottom part because the Kp value is actually an easier answer to give. You have to remember the only thing that changes the value of Kc, which also applies to the value of Kp, because remember Kp and Kc do share the same basics, which are that they are equilibrium constants. The only thing that changes K values, whether it's Kp, Kc, doesn't matter, is the temperature. Now the question says the same temperature. Because temperature doesn't change, the K value, which is temperature dependent, cannot change. Remember that temperature is the only thing that will change the K value, whether it's Kc or Kp. So the effect on the value of Kp is that it has none. There is no effect on the value of Kp. Because since this is carried out at the same temperature, the only thing that changes is the volume, then that means that the value of Kp will not change because temperature doesn't change. So that's the first part. That's the easy one, the easy part of the 2 points, because this is a 2-point question. That's the easier one to answer. Now, the effect on the yield of ammonia does take a little more thought process. So let me walk you through the thought process here. First of all, what are we doing? We are using a container of a smaller volume. The reaction is repeated with the same starting amount of nitrogen and hydrogen, meaning we are not changing the moles, but we are using a smaller volume. Smaller volume, so if the volume goes down for our container, That means a few things. That means concentrations will go down, but we're not looking at concentrations because we're using Kp. We're doing a reaction that's completely gas-based. So we can look instead at partial pressures. Because the volume is smaller, that means that we are increasing pressure. Remember, the smaller the volume because of gas loss, the smaller the volume of a container, the higher the pressure of the gas because there's less room for those same number of moles, and so the pressure increases. And remember what we talked about in Le Chatelier's principle. When pressure goes up, we're going to shift the equilibrium to the lower number of moles of the gas. In this particular reaction, we have 2 moles of the gas on the product side and 4 moles of a gas in the reactant side. There are more gas moles in the reactants than there are in the products. So when pressure increases, the Chatelier principle says that we are going, or the equilibrium is going to shift to counteract the change. So we're going to shift the equilibrium to get less moles or less pressure. How do we get less pressure? We shift the equilibrium to the side with the less moles of the gas. Since the reactants have 4 moles of the gas and the products have 2 moles of the gas, because we increase pressure by decreasing the volume, this equilibrium is going to shift to the right to where there are less moles of the gas, which is going to lower our pressure. Again, Le Chatelier's principle. We're going to shift the equilibrium is going to shift to counteract the change. So it's going to shift to the right. So we're going to get less, or we're going to get a right shift of the equilibrium, meaning we are going to get more ammonia. Because we're shifting the equilibrium to the right, we're shifting towards the products, we're going to get more ammonia. Meaning, how does it affect the yield of ammonia? The yield of ammonia is going to increase. This is the explanation, but you don't need to give the explanation because our command word was state. All we need to know is that because volume decreases, pressure increases, which according to Le Chatelier's principle will shift the equilibrium to the right towards the lower number of moles of a gas, meaning we're going to get more ammonia, so the yield of ammonia will increase. We're going to get more ammonia out of this reaction. And again, the effects on the value of Kp are going to be none because the only thing that affects the value of the equilibrium constants, whether it's Kp or Kc, is temperature, and they tell us the temperature stays the same. So the yield of ammonia increases, value of Kp stays the same, or there's no effect on the value of ammonia. And that's pretty much it for 8.4. Again, it's all the same stuff we saw with 8.3 with the equilibrium constant, with the addition of the mathematics that we're going to do for partial pressure and the mole fraction. That is it for section 8.4. I will see you all in the next video.